A single guitar chord rings out across the open Martian surface. The high notes leap away first, sharp and immediate. The bass note lags behind, dragging, arriving seconds after the hand has already lifted off the string. One chord, two separate arrivals. The air out there does not keep its promises. 10 meters apart, two astronauts try to hold a conversation with their suit radios switched off. One speaks a single sentence. The vowels arrive first, quick, clear, almost too fast. Then, a fraction of a second later, the low rumble drags in behind it, smeared, delayed, like an echo that should not exist. The sentence lands in two separate pieces at two different times. No amount of careful listening can put it back together the way it was spoken. On Mars, your voice comes apart before it reaches the person standing next to you. That is not a glitch. That is the atmosphere. On Earth, every pitch of sound travels at almost exactly the same speed. Bass and treble, deep rumble and sharp hiss, all of it moves through the air at roughly 343 meters per second. Earth's atmosphere is dense enough and simple enough in composition that molecular collisions carry every frequency uniformly. A chord stays a chord. A sentence stays a sentence. The internal timing between high and low never breaks. Mars has no such guarantee. Picture a marching band spread across a football field, every instrument starting the same note at the exact same instant. On Earth, the trumpets and the tubas reach the far end of the field together, still locked into the same chord they started as. That is what uniform sound propagation buys you, a promise that a unified sound stays unified no matter how far it travels. Now imagine the trumpets sprint ahead while the tubas fall behind. By the time the sound crosses the field, what left is one clean chord arrives as a smeared, staggered mess. The low notes are still trailing in behind the high ones. That second version is not a hypothetical. That is what every sound on Mars actually does. Earth never asks its air to make this choice. Mars's atmosphere is almost entirely carbon dioxide, roughly 95%, compared to Earth's 0.04%. It is also extraordinarily thin, less than 1% of Earth's atmospheric pressure. In an atmosphere this sparse, sound waves are no longer colliding with enough molecules packed closely enough together to move as a single uniform wavefront. High-frequency sound has a short wavelength, short enough that it slips between the widely spaced CO2 molecules with relatively little resistance. Low-frequency sound has a long wavelength. That longer wavelength interacts with the same sparse gas differently. It loses energy at a different rate as it travels. The two ends of the audible spectrum are, in effect, running through two different obstacle courses laid out in the same air. Mars does not have one speed of sound. It has a spread of speeds. The average is close to 240 meters per second, about 30% slower than Earth's 343. That number alone would just mean speech takes longer to arrive, the way a shout across a canyon takes longer than a shout across a room. But the average conceals the actual mechanism, and the actual mechanism is where the real story lives. The instinctive guess is that Martian air behaves like a volume knob turned down. Thinner air, quieter sound, everything running a little slower, but still arriving together the way it left. Turning it down a volume knob does not touch the internal timing of a song. The bass line and the melody stay locked to each other. They simply both get quieter. By that logic, Mars should sound like Earth, just muffled and slightly delayed. A chord delayed as a whole is still a chord. That instinct is wrong. And the way it is wrong is the entire problem. A uniform delay would preserve a sound's internal structure. Every frequency would still arrive locked to every other frequency, just later. The volume knob model would hold. What Mars does instead is not uniform. It is frequency dependent. The different pitches inside a single sound source do not travel together. They physically separate because they are moving at different speeds through the same thin CO2-heavy air. A spoken word does not simply arrive late, it arrives broken. A broken word is a mystery no listener can solve by trying harder. There is a second way to picture this, closer to something most people have actually experienced. Think of watching a slow-motion video where the audio track has slipped slightly out of sync with the picture. The classic bad lip sync problem.
Normally, that desync is constant. Every syllable is off by a fixed amount. Your brain can sometimes learn to compensate for a fixed offset. Martian speech desync is not fixed. It grows or shrinks depending on the pitch of what is being said. Within a single sentence, some syllables slip further out of alignment than others. It is not one desynced video, it's dozens of micro-desyncs stacked inside every phrase, each one different, none of them predictable from the last. The brain has no patch for a desync that keeps changing shape. Human speech depends on tight timing more than most people ever notice. A single vowel is not one frequency. It's a cluster of frequencies called formants, layered together with the low resonant hum of the voice underneath. On Earth, that cluster moves as one unit from mouth to ear, arriving as a single coherent packet the brain can decode instantly. On Mars, the cluster splits apart mid-flight. The high components race ahead, the low hum trails behind. By the time both pieces reach a listener, they are no longer stacked the way they left the speaker's mouth. The acoustic signature of the vowel has been physically pulled apart by the same distance that was supposed to simply carry it. Speech is not just sound, it's timing, and timing is exactly what Mars cannot preserve. There is a third way to see the same failure, this time as a race. Imagine a relay race. Every runner starts at the same instant from the same line, but each lane has been secretly assigned a different maximum speed. The fast lanes, the high frequencies, pull ahead steadily from the first stride. The slow lanes, the low frequencies, fall behind. Not because anyone tripped or hesitated, because their lane was simply built to be slower. They all started as one synchronized field of runners. They finish spread across the track, arriving in a ragged sequence instead of a single unified line. That ragged finish is what a spoken sentence looks like by the time it reaches a listener on Mars, a field of frequencies that started together and finished scattered. 3 analogies, 1 physical cause. At what distance does that separation actually break a sentence? Not 100 meters, not 50. Acoustic modeling built from real Martian atmospheric data suggests the frequency split becomes audible over distances as short as a few tens of meters, well within normal conversational range. A person standing as close as you would stand to a friend at a bus stop is already inside the zone where a sentence starts coming apart. That number is small enough to be personal. It is the distance between two people who assumed they could just talk. For a long time, this was theory. Models built from atmospheric composition and pressure data run on computers, never tested against real Martian air. That changed in February 2021. NASA's Perseverance rover landed in Jezero crater carrying something no previous Mars mission had, a working microphone. The SuperCam instrument recorded the sound of Martian wind moving across the crater floor. It recorded the sharp crack of the rover's own lasers striking rock over and over as it analyzed mineral samples. For the first time, humanity had actual audio captured on another planet, not a simulation, not a computer model extrapolated from density readings, a real recording of real sound moving through real Martian air. The theory finally had a witness. Acoustic scientists, led by French researcher Baptiste Chide, pored over that recording. The frequency-dependent speed differential predicted by decades of atmospheric modeling was there in the real data. It was hiding in the timing of the laser strike cracks recorded at different distances from the microphone. High-frequency sound was moving measurably faster than low-frequency sound, exactly as the models had predicted. A theoretical curiosity, built from equations and assumptions about CO2 molecules, became a confirmed physical property of another world, measured directly rather than inferred. Mars had been doing this the entire time. Nobody had heard it happen until 2021. The distortion problem does not travel alone. Mars's thin atmosphere also means sound loses energy fast as it moves outward.
It spreads its limited acoustic power across the same thin, sparse medium that is already splitting it apart by frequency. The same shout that carries clearly across a football field on Earth would be almost inaudible at that distance on Mars, swallowed by the low air pressure long before the frequency splitting even becomes the dominant problem. Speech on Mars is not just coming apart in time, it is fading out in volume at the same time, from the same cause. The signal becomes simultaneously quieter and less coherent the farther it travels. Two failures, one atmosphere, one sentence caught between them. There is a third failure stacked on top of the first two, and it matters more than either alone. Every acoustic warning system, every alarm, every verbal emergency signal humans have ever designed assumes an Earth atmosphere carrying the sound. A siren's rising pitch, a shouted warning, the specific frequency range engineers chose because human ears parse it fastest. All of it was tuned for air that does not split frequencies apart. On Mars, that same alarm would arrive distorted and delayed, its carefully engineered urgency scrambled by the same physics scrambling ordinary conversation. A warning designed to be instantly recognizable on Earth could arrive on Mars as a smeared, ambiguous noise, too late and too unclear to serve its one purpose. Safety-critical communication on Mars cannot lean on unmediated sound at all. It has to be electronic, or it does not work. A warning that arrives late is not a warning. The obvious fix seems simple. Speak louder, use a megaphone, project the sound farther the way people do in any noisy environment on Earth. More volume should mean more range. It does not fix anything.
Amplifying a chord does not stop it from splitting apart. The separation between high frequencies and low frequencies is a function of distance and atmospheric composition, not loudness. The same physics that pulled the guitar's bass note behind its treble note happens whether the string is plugged softly or struck hard, whether the sentence is whispered or shouted through a megaphone. A louder sentence still comes apart into the same staggered pieces, just louder pieces, arriving just as broken as the quiet version. You cannot shout your way around a problem built into the air itself. There is no acoustic workaround. There is only a different channel entirely. Volume was never the variable that mattered. Every realistic architecture for a human presence on Mars already accounts for this. Habitats, surface operations, colony infrastructure, every mission plan that gets past the drawing board. Astronauts do not rely on open-air speech beyond the shortest distances, even standing close to each other during an EVA. They rely on radio, routed through the suit systems for anything that actually matters. Instructions, warnings, coordination, the ordinary back and forth of two people trying to get a job done. Radio waves are not acoustic, they are electromagnetic. The composition of the atmosphere outside a helmet does not touch a radio wave by a single microsecond. A radio wave does not need molecules to collide against. It does not need a medium at all. A voice converted to a radio wave and back into sound inside another person's helmet never passes through the thin Martian air in between. It skips the exact part of the planet that breaks speech, arriving intact on the far end regardless of distance or atmospheric weirdness. A voice on a wire skips the broken air entirely. The actual solution to a Martian conversation is to stop attempting one acoustically at any real distance. Open-air sound becomes a short-range, low-fidelity signal at best. Useful for a shout across 3 meters to get someone's attention, useless for anything resembling an actual conversation. Everything that matters moves through radio instead, as a matter of engineering necessity rather than convenience. That is engineering, not convenience, which produces a strange picture. 2 colonists standing 3 meters apart, both capable of shouting, both wearing helmets equipped with microphones and speakers, talking to each other through a radio link instead of the air between them. Not because the radio is more convenient, because the air genuinely cannot carry their words intact past a short distance. A closeness that should feel unmediated instead runs through a machine every single time for as long as anyone lives there. That is the honest price of a Martian hello. There is a sharper irony buried in this. The moon has no atmosphere at all, a true vacuum where sound simply cannot exist in any form. That is at least a clean problem. No air, no sound, no ambiguity, no false hope that a shout might carry. Mars is stranger. It has just enough atmosphere to make sound possible, and just enough atmospheric weirdness to make it barely functional. Mars promises speech, and then quietly withdraws the promise, one separated frequency at a time, over and over every time someone tries. A planet with genuinely no air would have been the more honest problem. Mars teases, it does not deliver. None of this is limited to Mars. What makes speech, music, and every recognizable structure of sound possible on Earth is not a universal law of physics. It is a specific property of Earth's atmosphere, dense enough and uniform enough in composition that every frequency stays locked to every other frequency as it travels from source to ear. That reliability is a gift of this particular planet's air, not a guarantee written into the laws of nature generally. It is easy to mistake a local convenience for a cosmic default until you leave the one place where it happens to hold. No atmosphere owes speech anything. Change the atmosphere, and the rules of sound change with it. Venus, with its crushing, near-total CO2 density under 90 times Earth's surface pressure, would distort sound in its own specific way, probably in the opposite direction from Mars, too thick rather than too thin, but no less hostile to a sentence staying intact. Titan, wrapped in thick nitrogen and methane haze at temperatures near minus 180 degrees Celsius, would carry sound still differently, shaped by its own molecular mix and its own pressure. Any future colony built inside an atmosphere unlike Earth's will inherit its own version of this problem, a version of the human voice that no longer holds together the way it always assumed it would. Every atmosphere writes its own rules for the human voice. The guitar chord on the Martian surface never sounded broken to the person who struck it. It sounded normal for exactly as long as the string was ringing near their own ear, close enough that the split had not yet had room to happen. It only came apart in the distance between the hand and whoever stood far enough away to hear it separately. A treble note arriving on time, a bass note still arriving seconds later, alone.